Welcome to this interesting and short topic, rates of reactions. So we're going to discuss this topic by starting with the introduction, then we'll move to factors that affect rates of reaction. When we get done, we're going to take a look at a core concept called chemical equilibrium. When we get done, we're going to end with other reactions. So here we're going to discuss just a few ideas, knowledge about other types of reactions in chemistry. In this video, we're going to do introduction and factors that affect rates of reaction. Then in the next and last video, we're going to take a look at chemical equilibrium and other reactions. So we're going to discuss this topic in two videos, this one and the next. So what is a rate of chemical reaction? So the rate of chemical reaction is just the speed at which the reaction takes place. So the formula for rate is change in the amount of reactants or product over change in time. Okay, so what you just need to know is how much the reactants are changing or how much the products are changing. You can't measure both of them simultaneously. It might be a waste, or it might just bring complexity. So you just have to concentrate on one, either a reactant or a product. So when you want to measure the rate using the product, concentrate on the product. When you want to measure the rate using the reactant, concentrate on the reactant. So in an exam, it might be time consuming to write this entire formula. So we use this symbol to mean change. So we can write this formula as change reactants or products over change time. So forgive me for these words changing because it's a repetition. So it's supposed to be change time. Change reactants or products over change time. Now we go to measuring the rate of reaction. How do we measure the rate of reaction? So we can measure the rate of reaction by observing or measuring how quickly a product is obtained, how fast a product is obtained. So when we get reactants, there is no product, but when they start reacting, there will be a product. So now we can be measuring how fast that product is being made, or we can measure how fast reactants are used up. Since in a reaction, the reactants are going to be used up to form products, so depending on the type of reactants and the type of product, maybe we can concentrate on measuring how quickly the reactant is going to be used up. So I'm just going to show two simple apparatus demonstrating a simple reaction which involves a gas. So in this reaction, or in this setup, hydrochloric acid reacts with calcium carbonate to form carbon dioxide. So carbon dioxide is the product. So what we can do is we can use a gas syringe to trap carbon dioxide. As the reaction is proceeding here, a gas which is carbon dioxide is going to be formed and it's going to be kept in here. So the amount of gas that's going to be formed will be of a certain volume in here. So we can measure the increase in volume of the product as the change in product, which we can use in our equation. So when we plot, let's say as the reaction is proceeding, we get the volumes, and as the time is proceeding, so keep on recording the volume as the time is proceeding, and then we plot a graph of volume against time. We're going to have something like this, where here we have volume of the gas produced and here we have time. So what is happening here is, as the reaction was proceeding, the volume was increasing. Okay, so as time increases, the volume is also increasing. Then a point was reached when, as time kept on increasing, the volume was not increasing. So what we can depict from here is the reaction at this point had stopped. Why? Because the time was increasing but the volume was not increasing, meaning that no more carbon dioxide was being formed. So the reaction was just from here to here. So to measure the rate of reaction, you just have to get a time maybe at this point and a time at this point, and also the corresponding volume at this point and at this point. Then you subtract the volume at this point from this point divided by the time at this point and at this point, which is basically the gradient of the graph at this point. So the gradient is equal to the rate of the reaction. So another way in which we can measure the rate of reaction is how quickly the reactants are being used up. We can have this arrangement. So here we have a mass balance, which of course measures the mass. Then here we have cotton wool, whose purpose is to act as a stopper. By that it means in case of any tilting, the hydrochloric acid or the liquid part or whatever is making up the reactant should not come out of here. Okay, then this cotton wool also has a special feature. It allows the gas to escape. So as the reaction is proceeding, carbon dioxide is being produced. This carbon dioxide is going to penetrate through the cotton wool and it's going to go up. So the mass of the entire apparatus here is just going to be the mass of the reactants remaining, because the carbon dioxide, which is the part of the reactants that are being used up, is escaping. So when you keep on recording the masses as time progresses, and then you plot the graph of mass against time, you're going to have something like this. So what is happening here? So as the reaction was proceeding, the mass was decreasing, which implies that the reactants were being used up. They were being converted to carbon dioxide, which was escaping the apparatus. So as the reaction proceeded, a point was reached where the reaction ended. Why? Because as you can see here, as time increased, the mass was not changing, meaning that there was no any reaction. There was no the reactants were not being converted to carbon dioxide anymore. So the reaction ended here. Again, if you want to measure the rate of reaction, you can just get 2 points on this graph here and here. You get the time and the mass, the time and the mass, you subtract them, and again the gradient of this graph is the rate of the reaction. Next, we're going to take a look at what is called the collision theory. The collision theory. So this theory states that for a reaction to take place, the particles of the reacting substances must move and collide with each other with a certain amount of kinetic energy. So they have to move and bump into each other with a certain amount of energy. With this theory, the number of collisions taking place per unit time depends on the number of particles, meaning that if the particles or the number of particles are increased, the number of collisions also increase. You can picture this as a small room that has people, and these people are supposed to be moving. So if the number of people is not that big, you expect them not to collide that much. But if the number of people is that big, then there will be too much collisions. That's what the collision theory states. So with this collision theory, what factors can increase or reduce the rate of a chemical reaction based on this understanding? So the first factor is concentration. The second is temperature. The third is pressure. The fourth is surface area or size of a particle. And the last one is something that is called a catalyst. So we're going to analyze how each of these factors influence the rate of reaction. The thinking is going to be based, or it's going to be on the perception of the collision theory, the theory of particles colliding into each other. So we're going to start with concentration. Concentration, we're not talking about concentration of products, but concentration of reactants. We can't, when the reaction is about to start, we don't have products, so we don't talk about concentration of products, we talk about concentration of reactants. So when concentration is increased, meaning that the number of reactants are increased, the rate of reaction also increases. This is because the number of particles in the solution increases, and meaning that the particles are going to collide with each other effectively. Okay, so if we do a graph of let's say there's this hypothetical experiment of where we have hydrogen peroxide. So this hydrogen peroxide, it's going to be decomposed to form oxygen. Okay, so depending on the concentration, if the concentration is low, this is how the graph is going to look like. But if the concentration is high, this is how the graph is going to look like. So which graph shows a faster reaction? So if you take the time here and the time here, if you go down here, the time here and the time here, you are going to see that the time here is lower than the time here. This reaction is ending here and this is ending here. Since this is ending in a shorter time than this has a higher rate. So this is just to show us, okay, of course this was experimented on, so this is how to read the graph, and this of course shows that concentration of reactants, the increase in concentration of reactants increases the rate of reaction. Next is temperature. How does temperature affect the rate of reaction? If you can recall, when we're doing diffusion, these things should be in the same line, the same kind of thinking. So temperature is just the measure of the average kinetic energy of the particles. Kinetic energy is moving energy. So temperature is just the measure of the average moving energy of the particles. When temperature is increased, the rate of reaction also increases. Okay, why? This is because the particles gain kinetic energy and move faster and collide effectively. So they move faster, so they are going to collide effectively, and even the number of collisions are going to be increased because they are moving faster in a short time. The next is pressure. So how does pressure affect the rate of reaction? Pressure becomes an important factor only in reactions involving gases. In reactions that don't involve gases, pressure is not an issue. So when pressure is increased, the rate of reaction also increases. How? So the way the rate of reaction increases is the volume reduces. For those who remember the gas laws, so according to those laws, when pressure is increased, volume reduces. So when you increase pressure, volume reduces. Since the volume has reduced, it means the particles are going to be close. So they will be forced to be closer, meaning that they will be bumping into each other more often. Next, we look at this interesting one, surface area, or the size of the particle. So particle size usually refers to the particle of a solid reactant. Just like pressure is about gases, particle size or surface area usually refers to solid reactants, not liquid, not gaseous reactants. The rate of reaction is faster when the size of particles is small. This is because a small size particle has a large surface area. So what does it mean to have a large surface area? So a large surface area can be perceived to be okay, let me put it in this way. When two particles are colliding, the outside surface of the particles are the ones that contribute to the reaction. So if a particle is small, it means most of its surrounding or most of its external environment, not environment, most of its surface, let me just use that word, I wanted to run away from surface. most of its surface is going to participate in that collision. Okay, so as compared when something is big, it's like if you get a matchstick, then you try to start a fire on a log, like you want to put a log on fire. It might be easier if you just get small branches, then you put you put them on fire. It's going to be easy because most of their surface is going to be exposed to that fire. So that's what surface area is all about. The smaller the surface area, I mean the smaller the particle size, means the greater the surface area, therefore the greater the reaction. Finally, we look at a catalyst. So a catalyst is a chemical substance which changes the rate of reaction but remains chemically unchanged at the end of the reaction. So it will change the reaction, it will change the speed of a given reaction, but itself won't be changed. That's a catalyst. In short, it doesn't participate in the actual reaction, but it speeds up the reaction. A catalyst usually speeds up the reaction by lowering the activation energy of the reaction. So there is this concept of activation energy. So the activation energy, the symbol is EA. Activation energy is basically the minimum energy required to start a reaction. So remember, according to the collision theory, it talks about particles having a certain amount of kinetic energy for a reaction to occur. That minimum amount that is needed for a reaction to occur is what is called activation energy. So what a catalyst does is it speeds up the reaction by lowering the activation energy. For example, if for this reaction to occur, 20 joules of energy is needed from each of the participating reactants. So what the catalyst is going to do is it's going to reduce this maybe to 10. When it does that, it means once these two participants have a certain have 10 kilojoules of energy, then they are going to collide and there will be a reaction. So diagrammatically, this is how to view the effect of a catalyst. So here we have energy level. So this axis for energy level, what it does, it tells us the different energies. So here we can have 0 joules, 5 joules, 10 joules, 15 joules, just like that. Then here it's just how the reaction is proceeding with time. So the way we're viewing this is in terms of energy. So we have reactants here. This is the energy of the reactants. So let's say this is 40 joules. So this is the energy of reactants. So for this reaction to occur, these reactants need to gain this activation energy. So maybe this is 80 joules. So they need 40 more joules for them to react. So they need this activation energy, which is the 40 joules more for them to react and then produce the product. So normally without a catalyst, they need to have this amount of energy, then they are going to produce a product. So when a product is produced, of course, the energy of the entire system reduces, meaning that the products are going to be at a lower energy, as you can see. Okay, so the products are always at a lower energy than the reactants. Now when you add the catalyst, this activation energy, instead of it, for example, being 40, the catalyst is going to lower it to 3. So the two reactants are just going to have, once they have this 20 joules of energy, then the products are going to be formed. This is how a catalyst influences the rate of a chemical reaction. This marks the end of this part of the topic. I'm sure the next video is going to be short. We are going to talk about chemical equilibrium and other important chemical knowledge about reactions. Happy solving.